So let's start with the vector equation of a circle in 2 dimensions. We've seen it before, but we saw it when we were doing complex numbers. Remember we said we could write the modulus of z minus z naught would represent, that's going to represent a circle. So all we really were doing there was writing down the vector equation of a circle. So that's it in 2 dimensions. So we have actually seen that already. So we know the centre would be v naught and the radius would be r. Just to prove that it does give us our circle, let's rewrite that in component form. So I'd have x minus x naught in the I direction, y minus y naught in the j direction is equal to r. If I square both, so I'm finding the magnitude squared, so it gets rid of the square root, then I end up with my traditional x minus x naught squared plus y minus y naught squared is equal to the r squared, which we recognise to be the Cartesian equation of a circle. To take it a step further, cos squared plus sine squared, remember of course is 1. So r squared cos squared plus r squared sine squared is r squared. Now what that means is we can come up with a parametric form of a circle, and I've written it in components above and below so it looks like the vector. So x is x naught plus r cos theta, y is y naught plus r sine theta. So that becomes the parametric equation of a circle, but now I've written it as vectors. So the parametric is sort of like the intermediate between the vector equation and the Cartesian equation. It sort of goes in between. So show that this actually represents a circle. Now you notice I'm doing a dot product here, but it's the same in both. Now remember, u dot u is modulus squared. So that becomes the modulus of r minus 2i plus 3j squared is 12, square root of both sides, and I've got a vector equation of a circle. So I can see that its centre is 2 minus 3, its radius is 2 root 3. If I had to find a vector equation of the tangent to the circle, so here's a picture of it. The circle's got a radius 5, the point 3,4 would be on the circumference somewhere, and I've just drawn in the tangent. We want to find the vector equation of that line. So the vector PR, so r is just some random point on that line, would be r minus 3i minus 4j, head minus tail. We know that that's perpendicular to the radius. Now the radius I could write as the vector 3i minus 4j. So another way I could write the vector equation, because we know the radius is perpendicular to the tangent, well that tells me the dot product of these 2 vectors must equal 0. So it's a different way of writing a vector equation, but that is a vector equation of that tangent. So I've expressed it using vectors, but I've gone dot product rather than the traditional way of doing it. I would imagine that would have to be an acceptable answer for something like that. So what is the Cartesian equation of that tangent then? Okay, let's go back to that dot product, but now I'll rewrite the first one in component form. So x minus 3i plus y minus 4j, and we're saying that dot product is 0. So therefore, 3 times x minus 3 minus 4 times y minus 4 must equal 0. And there's the equation of our line. 3x minus 4y plus 7 is equal to 0. All right, let's move to 3 dimensions. But I'm jumping straight to the vector equation of a sphere. And the reason I'm jumping straight to that is because, look, the equation does not change. And that's a beautiful thing about vector equations. Remember, the vector equation of a line was the same in 2 dimensions as it was in 3 dimensions. And theoretically, if you could, obviously we can't draw it, but it would be the same in 4 dimensions, 5 dimensions, however many dimensions you want to go. So here, all we're saying is the distance from v to v naught is a constant r. Well, if you're not talking about 3 dimensions, there's no reason why you have to stay in the same plane. That vector could go in any direction. So we now get a sphere rather than a circle, but the exact same equation. So the centre would be v naught and the radius would be r. The magnitude then, let's break it into component form. I'm going to come up with the Cartesian equation, and you'll see what we get. Again, it's very similar to the equation of a circle. All we've done is we've added in z minus z naught squared, the same as when we looked at the distance formula. All we did was we added in the z minus z naught squared. The midpoint formula, all we added in was the Z1 plus Z2 coordinates. We're just pushing it through to a third dimension. So there's our Cartesian equation of a sphere. You don't need to know this bit, but I thought for the sake of completeness, I'll put it there. But that would be the parametric equation of a sphere. If you look at it closely, hopefully you can see what's happening there. They've got a common factor of r cos theta, the x and the y. So if I went cos squared plus sine squared, I get r squared cos squared. So the x squared plus the y squared would be r squared cos squared theta. But now I could go with the z squared, that would be r squared sine squared theta, and then you get the x squared plus y squared plus z. But as I say, you don't need to know that, but I thought it'd be nice to put there to sort of complete the set. So we have two spheres, but if you were to push two spheres together so that they intersect, then they would intersect in a circle. I mean, initially they would just touch at a point, but as soon as one overlaps the other, that plane that they intersect on would have to be a circle. I've made the numbers nice here, so it's going to be good to work out. But upon which plane then would the circle lie? And, oh, wasn't that lucky? Look at that. X plus 2 squared will cancel, and y plus 3 squared will cancel. So I get z plus 2 squared minus z minus 4 squared is 9. So it's on the plane, z is equal to 7 on 4. All right, what would be the equation of that circle then? Well, we know the equation of the sphere. X plus 2 squared plus y plus 3 squared plus, doesn't really matter which one I put it in. So I've gone with the z on 4 minus 4 squared is 16. Push it out, I've got no z anymore. So I now have the equation of a circle. X plus 2 squared plus y plus 3 squared is 175 on 16, which would be a circle on the plane z equals 7 on 4. And so its centre, minus 2 minus 3, z's a constant 7 on 4, and the radius is still just the square root of that number there, so we get 5 root 7 on 4. Find the intersection point of the sphere and the line. So now imagine that tennis ball and a knitting needle. And so if you were to get a knitting needle and thread it through the tennis ball, the line's going to still meet in 2 points, the same as it would with a circle. Well, no different, I'll just solve them simultaneously. I've substituted the r into our magnitude, modulus, call it what you will, of r minus I minus 4j is 4. So I've just subbed that in. And if I group the i's and the j's and the k's together, we end up with this lovely expression. So we're saying the magnitude of that is 4. So lambda squared plus 4 squared, plus 2 squared, so that's 4. And then expand out the 3 minus 2 lambda all squared will be 16. I end up with a quadratic. That's good, because I was expecting 2 answers. Oh, didn't say they were going to be nice numbers. That lambda is 6 plus or minus the square root of 51 on 5. So I now know what lambda is. I can substitute it in. Now, the equation of the line, but I've written it in parametric form, or vector form if you like, to make it easier. So I'm looking at it and going, oh, well, x would equal 1 plus lambda. Y would equal 2. Oh, there is no lambda with the j's, so it's just 2. Z would equal 3 minus 2 lambda. So I just simply substitute in the lambda that I found into that, and I have my coordinates of the 2 points to separate them out. We end up with 11 plus root 51 on 5, 2, 3 minus 2 root 51 on 5, and 11 minus root 51 on 5, 2, 3 plus 2 root 51 on 5. But the idea is, well, I guess I'm getting at is, the ideas are no different. Right? We're just pushing it through to a third dimension. Yes, some of these calculations get a bit more interesting. This one here. I stole this question from the sample paper that NASA put up on their site. It was question 15, so second last question towards the end. So I think we're looking at here what they're sort of saying would be one of the more challenging questions, maybe. So V is a position vector of a point P, and that point is on the sphere. Sphere has centre C and radius R. So in other words, the vector equation for that would be V minus C is equal to R. And C is the position vector OC. Do not prove this. The equation of a line L, which also passes through P, in the direction of the vector M. So W, that's this new line, will equal V, because V is on the line, because it's going through P, and it's in the direction of M, so it'll be V plus lambda M. Find the values of lambda that correspond to the intersection. We can see from what they've asked, it's not going to be a nice, lovely number or something like that. It's going to be in terms of V, C, and M. So just drawing a picture here to try and get my head around what's going on. So I've got a sphere. P is sitting on the, I guess you still call it a circumference, the surface of the sphere. There it is there. And we know its distance to the centre is R. The line, the knitting needle going through the tennis ball, the line is going through, cuts it in 2 points, and we're saying the other point we're going to call W, because we know W lies on this line. Okay. And we know the distance will also be R, because if it's on the surface of the sphere, the radius is going to be constant no matter where we put the point. So we know, first thing we know there, vector equation, W minus C is equal to R. So if I just substitute in the equation of the line for W. So I've now got V plus lambda M minus C is equal to the radius. Well, I've rewritten it using that idea of U dot U is equal to the magnitude squared. So that's what I've done here. If you like, I've squared both sides, so I've made this magnitude squared, but rewritten it as U dot U. So in this case, V minus C, grouping them together, plus lambda M, dot V minus C lambda M. Expanding that out, and remember, when you're expanding out the dot product, it's not a vector times a vector, it's a vector dot product with the vector. Okay, so expand it out like normal. V minus C with V minus C becomes V minus C dot V minus C. Twice the product. Now, lambda's a scalar, so I can just go twice lambda, that's fine. But then I have the product of V minus C with M, they are vectors, so it must be V minus C dot M. And then the last one, lambda squared's fine because I'm just multiplying two scalars together, but then it'll be M dot M is equal to the radius squared. V minus C dot V minus C, magnitude of V minus C squared. And also at the other end, M dot M, magnitude of M squared. So that's what I've done there. Okay. But hang on a sec. V minus C, we know that's equal to the radius. So I've now got R squared on both sides of the equation. Well, they'll cancel out. And I'm left with 2 lambda V minus C dot M plus lambda squared magnitude of M squared is equal to 0. Remember, we're trying to make lambda the subject here. We're trying to find lambda. They have a common factor of lambda. Let's pull it out. So lambda outside of 2 V minus C dot M plus lambda magnitude of M squared. So either lambda is equal to 0 or this other wonderful expression which satisfies the question. Remember they said put it in terms of M, C and V. Well, I've done it. It's not a nice neat number, but it is in terms of M, C and V. So I'm going to leave it like that. That was just part A of the question, of course. Deduce then that the line L would be a tangent if and only if M dot V minus C is equal to 0, and then give an interpretation of what this means geometrically. Well, if it's now a tangent, that knitting needle now is not pushing through, it's just sitting on the ball. So W and V, if you like, are the same point, is another way of thinking about that. Okay? Well, that means V plus lambda M is equal to V. Well, that means lambda is equal to 0. So if there's only one point of intersection, if it's a tangent, lambda has to equal 0. That's fine for the left-hand side of what we proved here. lambda was equal to 0, but it always has to be 0 if this is going to be a tangent. So therefore, my right-hand side here, lambda equals 2m dot c minus v over magnitude of m squared, that also has to equal 0. Well, if I've got a fraction equaling 0, it must be the top of the fraction that equals 0, and I have what they've asked for. So m dot v minus c is equal to 0. Interpret that geometrically. Hang on. I'm saying the vector, which is in direction m, that was our line, remember, which we've now called a tangent, dot a vector, v minus c, is equal to 0. Those two vectors must be perpendicular. In other words, it's exactly the same as what we saw in 2 dimensions, but now it's in 3 dimensions. The tangent is perpendicular to the radius. It's still true in 3 dimensions. Now, some other graphs. Before I go on to other graphs, I want you to remember that this is a topic on vectors. It is not a topic on 3-dimensional coordinate geometry, which in itself is a whole load of fun. But that's not what this course is about. So we're only going to get lines, circles. That's what they've spheres. That's what they've specified in the syllabus. But just for the sake of interest, okay. Now a plane. Oh, of course we could get planes because we saw those perpendicular to that. But it's like I want to call it linear, but it's not a line, it's a plane. But it's like our linear function where all of the pronumerals were to the power of 1. So anything where you've got a simple adding of terms, that'll always be a plane. So the ones that were parallel to the xy, for instance, where z is equal to a constant. Well, okay, that's fine. Still satisfies this. A and b were just 0. So if you've got other numbers for a and b, then that plane comes through at an angle. There's a hemisphere. Again, notice the similarity with 2 dimensions. All we've done is we've pushed through to a 3rd dimension. We've added another variable, and it's still the square root of r squared minus x squared, now minus y squared. That if it's on the xy plane. If it was on the xz plane, then it would be y equals r squared minus x squared minus z squared, and so on. A paraboloid. This one opens in the z direction, if you like. So if you think of it like a, well, I don't know, what would that thing be? Don't say paraboloid. I'm just thinking of it like I don't know, say a flower or something anyway. But the open part, okay, is in the parallel to it's going in the z direction is what we're saying. So that would be z equals x squared plus y squared. A cone would be some constant times the square root of x squared plus y squared. A hyperboloid, but a hyperboloid of one sheet. And with one sheet, one of the pronumerals is negative. So you get negative z squared. If 2 of them are negative, you still get a hyperbola, but now you get the 2 sheets, so you sort of get the other bit. Well, it really becomes fun now. And I've written this one in parametric form. You get the helix, or a spiral. So you get that one there is 3 sine 5t, 3 cos 5t, and t for the parameters. And it just spirals up. I say, we don't actually need to know those. I just thought it was interesting. 5G will finish off our little topic.